In this video, we solve problem 9.2.6-T from Essentials of Statistics 6th edition by Mario Triola. The problem statement says, a study was done using a treatment group and a placebo group. The results are shown in the table. Assume that the two samples are independent simple random samples selected from normally distributed populations, and do not assume that the population standard deviations are equal. Complete parts A and B below. Use a 0.10 significance level for both parts. Now we're told that the treatment group will have a mean represented by mu sub 1, and the placebo group has a population mean represented by mu sub 2. We've got sample sizes, we've got sample means and sample standard deviations for both samples. In part A, it asks us to test the claim that the two samples are from populations with the same mean. First, it asks for the null and alternative hypotheses. Well, if the claim is that the populations have the same mean, that means the claim is the same as the null hypothesis. So mu sub 1 is equal to mu sub 2. And if that's not true, mu sub 1 would not be equal to mu sub 2. So that would be our alternative hypothesis. Okay, great. And then we are asked for the test statistic T, and we're asked to round to 2 decimal places as needed. To do this, I'll share my paper with you. Now this is the test statistic T corresponding to the particular value of x sub 1 bar minus x sub 2 bar we have in our samples. So we're imagining taking the distribution of these sample means, the difference between these sample means, x sub 1 bar minus x sub 2 bar, which has that bell shape that's similar to our normal distribution and has a mean which is equal to the true population mean for that first population minus the true population mean for the second population. And then we're assuming that the null hypothesis is true in this case. So we're assuming that that mean is 0. So mu sub 1 is equal to mu sub 2. And then we're asking ourselves, is the value of x sub 1 bar minus x sub 2 bar that we have for our particular samples significantly high or significantly low? Oh, in our case, x sub 1 bar and x sub 2 bar can be subtracted like this. Let's see. X sub 1 bar was 2.35 and x sub 2 bar was 2.62. And that is equal to negative 0.27. And so we're saying to ourselves, okay, is this difference between sample means of negative 0.27 significantly low, given that the null hypothesis is true? In this case, the null hypothesis is saying that mu sub 1 and mu sub 2 are equal to each other. Well, in order to figure that out, we have to compute this test statistic T. So we're converting this distribution of x sub 1 bar minus x sub 2 bar to a student T distribution. Now remember, the student T distribution has the same basic shape as that normal distribution. It's just a little wider. The variation is larger. This standard deviation is more than 1. And it varies for different values of the sample size. We're trying to find this test statistic T right here that corresponds to a certain area to the left. And it turns out that this area to the left over here is going to be equal to that area to the left over there after we convert. Okay, so that's the point. That's what we're doing. So we're finding the test statistic T that corresponds to this x sub 1 bar minus x sub 2 bar, and that is done by using this formula over here. Now x sub 1 bar minus x sub 2 bar, that's what goes in our numerator. And we just saw that that is negative 0.27. And then we're subtracting the assumed value of mu sub 1 minus mu sub 2, given that the null hypothesis is true. Well, the null hypothesis is that those are equal to each other. So when we subtract them, we get 0. And then we're dividing by an estimate of the standard deviation of this distribution, which is given by the square root of this sum, and S sub 1 is the standard deviation for that first sample. And S sub 1 in our case was 0.93, S sub 2 was 0.56, N sub 1 turned out to be 29. We had 29 in that sample, and N sub 2 happened to be 35. So what we're going to have here is S sub 1 squared divided by the corresponding sample size, and then we'll have S sub 2 squared divided by the corresponding sample size, and that's going to give us some value. So if negative 0.27 divided by this expression here, so I can type square root of open parentheses 0.93 squared divided by 29, close parentheses for the first fraction. Then we want to add open parentheses 0.56 squared divided by 35, close parentheses for the second fraction, and we get this. We get a t-score, a test statistic t, of approximately negative 1.37. Now this is not a number of standard deviations below the mean, but it's similar to that. It's just the t-score that it corresponds to this area to the left being equal to that area to the left for the right number of degrees of freedom for this distribution over here. So that's negative 1.37, and we're asking ourselves, is that significantly high or significantly low? So let's enter that answer, rounding to 2 decimal places, negative 1.37. Great. And then they want the p-value, and they want us to round to 3 decimal places. Now, when you're finding a p-value for a test statistic t, it's necessary to use technology. The p-value, just as it was computed before, has to deal with the area in the tails beyond our test statistic. Now, in order to determine whether this area is the area we're looking for or double that area, we need to look at the null and alternative hypotheses. So we've got our alternative hypothesis in this case, which is mu sub 1 is not equal to mu sub 2. Since that's a not equal to sign, it doesn't matter if we're too high or too low. We're going to consider too high or too low significantly different from 0 here. And that's going to cause us to reject the null hypothesis. So if we've got a not equal to sign, that means we've got a two-tailed test. So in that case, the p-value is equal to the probability that t is less than this negative 1.37. Our test statistic t is less than or equal to negative 1.37. Or our test statistic e is equal to 1.37 positive, or positive 1.37, or greater than that. Because we're looking for values of the test statistic that are as extreme as ours on the left or on the right, or more extreme than ours. So it's the same as taking this area and doubling it because of symmetry. And in order to compute this, I'm going to use those t distribution functions in Excel. So we'll have 2 times t dot dist. And since I want the area to the left, I will type my test statistic. And I believe the next thing they want is the degrees of freedom. And then I think they want one other thing. I think they want either a true or a false or something like that. We'll look at it in Excel and see exactly what they want. So we'll type equals t dot dist, and I will choose this function, open parentheses. So I want the t-score, which is that negative 1.37. Then they want the degrees of freedom. And then they're going to want true or false for area to the left. So we're going to say true, we do want the area to the left. Now the degrees of freedom can be handled a couple of different ways. In order to decide on our degrees of freedom, we need to decide whether we want to be conservative or more accurate. So this function is asking for our test statistic t, the degrees of freedom, and whether we want the area to the left or not. And we're going to say yes every time. So we're going to type in true. Now, one way that you can get an estimate of the degrees of freedom is to use this rule. The degrees of freedom will be the minimum of this set. You've got two numbers, n sub 1 minus 1 and n sub 2 minus 1. So in our case, that's the minimum of, well, our first sample had 29 in it, so we could have degrees of freedom of 28. And our second sample had 35 values in it, so the degrees of freedom would be 34. The minimum of those two is 28. So if we want a conservative estimate here, we could use the degrees of freedom equal to 28. Now, if we'd like to be more accurate, we can use this formula instead. The degrees of freedom are given by a plus b squared over a squared over n minus 1, or n sub 1 minus 1, plus b squared over n sub 2 minus 1, where a and b are these expressions right here. A is s sub 1 squared over n sub 1, and b is s sub 2 squared over n sub 2. This obviously takes a little bit more computation, but it's actually pretty easy to program up in Excel. It's very easy to just type that in. So we could easily find the correct number of degrees of freedom and enter that here. So let's actually do this two ways. Let's find the p-value using this conservative estimate, and then let's this conservative estimate for the degrees of freedom, which is going to lead to conservative conclusions with our hypothesis test. And then let's do it with the more accurate estimate, or the more accurate value of the degrees of freedom below. Okay, so let's do conservative estimate first. So we'll put a 28 right there. So I'll type 28 and true here. And the p-value is twice that because it's a two-tailed test. And so we get approximately 0.18157 as our p-value, which when rounded to 3 decimal places as requested on MyLab Statistics is 0.182. Let's see if it likes that. Okay, great, it liked that just fine. Or we could use this more accurate number of degrees of freedom. So let me show you how to use Excel to write this up. Okay, so I've just typed in my x sub 1 bar, x sub 2 bar, S1, S2, N1, and N2, and I want to use this formula for the degrees of freedom. That requires that we compute A equals S sub 1 squared over N1, and I guess we should have extra parentheses here just to indicate that we're squaring that and then dividing by N1. And B is equal to S sub 2 squared over N2. Well, that can be computed pretty easily, so we'll type equals S sub 1 squared. You select that cell, put some parentheses here, and then we're dividing by N1. And then here we'll do the same thing. Have S sub 2 square it, and then divide by N2. And we get that for our A and our B. Now, if we look at our formula, I've got to have a plus b squared, and then I'm dividing by a squared over n sub 1 minus 1 squared plus b squared over n sub 1 minus 2 squared. I think I'll do the denominator separately from the numerator, and then we'll just divide those. So for my numerator, that's supposed to be a plus b quantity squared. So we'll open parentheses and we'll type a plus b quantity squared. And then for my denominator, I need a squared. Actually, I'll type it this way, open parentheses, a squared divided by the quantity n sub 1 minus 1. And then we're going to take b and square it. And then we're dividing by the quantity n sub 2 minus 1. It's a very small number. And the degrees of freedom are equal to this numerator divided by this denominator. And actually we get 44 for our degrees of freedom, which is quite a bit larger than that 28 degrees of freedom. So I'm just writing that down now over here. So our more accurate estimate, which is less conservative, is this degrees of freedom equal to approximately 44.075. Okay, so if that is my number of degrees of freedom, let's find the corresponding p-value. We'll have 2 times t.dist, open parentheses, and then we enter our test statistic, which I did not calculate on this screen, so I'll just use the estimate, negative 1.37. And then we want the appropriate number of degrees of freedom. This time I want to use my more accurate value of 44.075 and so on. And we say true, we do want the area to the left. We're going to take the area to the left of this guy. So that's this area here, and then we're doubling it because it's a two-tailed test. And so in that case, our p-value is slightly smaller. Our p-value is approximately 0.1776. And if I round that p-value, to 3 decimal places, I get 0.178. So notice it's just a little bit smaller than that because we are using this less conservative, more accurate value of the number of degrees of freedom. Okay, now let's go back to my lab statistics and answer their questions. Okay, so we're going to compare this p-value to our 0.10 significance level. That p-value is either 0.182 or 0.178. Either way, that p-value is greater than our alpha value. So we're going to fail to reject the null hypothesis. So it's either A or C. And then after we decide to fail to reject the null hypothesis, we have to think about what the original claim was. Let's see. What is the claim? It says, test the claim that the 2 samples are from populations with the same mean. So the claim happens to be the null hypothesis in this case. If we're failing to reject the null hypothesis, what we're saying is that the claim might be true. So we're going to choose A because it says fail to reject the null hypothesis, and there is not sufficient evidence to warrant rejection of the claim that the 2 populations or the 2 samples are from populations with the same mean. We can't say that we accept that the claim is true, but we can say that we don't have sufficient evidence to reject it in much the same way that we're saying that we can't accept the null hypothesis, but we can fail to reject the null hypothesis. Okay, now we're going to do a confidence interval estimate for testing the claim that the 2 samples are from populations with the same mean. So we're going to come up with the appropriate confidence interval. And then after we've come up with the appropriate confidence interval, we're going to think about whether or not 0 is in that confidence interval. Now, when we come up with our confidence interval estimate, we were asked to come up with the lower limit of that confidence interval to 3 decimal places, and the same thing for the upper limit. The lower and upper limits come from taking our best point estimate of mu sub 1 minus mu sub 2, which is x sub 1 bar minus x sub 2 bar, and then adding and subtracting the error from that, or the margin of error from that. And the margin of error is given by t sub alpha over 2 times the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. So this is an estimate of the standard deviation, and this is kind of like a z-score, but it's a t-score corresponding to a certain area in the tails. Now, we have to decide on what that area in the tails should be by thinking about whether we had a one-tailed test or a two-tailed test, and thinking about the significance level and all of those things that are related to the original confidence or the original significance level of our hypothesis test. So we were told at the beginning that for this test, our alpha was equal to 0.10. That's our significance level. And the question becomes, when I come up with this t sub alpha over 2, is this alpha equals 0.10 area in one tail or area in two tails? To decide, we need to look at the alternative hypothesis. Now, the alternative hypothesis in this case happened to be that mu sub 1 and mu sub 2 were not equal to each other. So that means we're dealing with a two-tailed test, which means this alpha area is split into two tails. So if I've got 10% of the area there, I want 5% of the area on this side and 5% of the area on this side. And when I'm looking for t sub alpha over 2, what I'm looking for is t sub 0.05. That's the t-score that has an area to the left of 0.05 plus the rest of this area. 10% of the area is in the tails. We're going to have 90% of the area in the middle. So the area to the left of this t-score is 0.95. Now we can find this area to the left using a t-distribution inverse function in Excel, but we need to know the appropriate number of degrees of freedom. So we had the conservative estimate of 28 degrees of freedom, or we had the less conservative estimate, which was about 44.075 degrees of freedom. We're going to get slightly different values for a t sub 0.05, depending on which number of degrees of freedom we use. But then once we find that t sub 0.05, that's going to go there, and then we can multiply by this estimate of the standard deviation. So let's do all of that. Let's do that in Excel. So I'm back in Excel again, and this time I want an area to the left of a t value to be 0.95. So I will type equals t dot inv, and we want the probability or the area to the left to be 0.95, and then we want the appropriate number of degrees of freedom. If we use the conservative 28 degrees of freedom, we get this. This is with df equals 28. I'm just putting that there as a note to myself. Or if I want the less conservative degrees of freedom that is more accurate, using that a and b in our formula, we'll do t dot inv again. It's asking for a probability of 0.95, and the number of degrees of freedom is right there. And we get a slightly different t sub alpha over 2. I'm going to write degrees of freedom approximately equal to 44. Okay, so those are our t-scores. Now we also need this estimate of the standard deviation. This estimate of the standard deviation has a and b in it. It's just the square root of a plus b. So we can find this estimate of the standard deviation by just taking the square root of a plus b, because we've already defined those in Excel. So let's go back to Excel. estimated standard deviation for our confidence interval is the square root of A plus B, close parentheses, and we get approximately that value. Well, our margin of error is either this t sub alpha over 2 times this estimated standard deviation, or it's this t sub alpha over 2 times this estimated standard deviation. Notice that our error is a little bit different, especially in that third decimal place. And then we're going to take that and we're going to add that and subtract that from x sub 1 bar minus x sub 2 bar. And that value can be typed right there. So I'm zooming out now so that we can see all the values. So I've got x sub 1 bar minus x sub 2 bar, and that gives me that value. So using our conservative number of degrees of freedom, our upper limit and our lower limit for our confidence intervals are x sub 1 bar minus x sub 2 bar plus this error, and then we have x sub 1 bar minus x sub 2 bar minus this error. So that's one possibility. And this is the slightly more accurate. There we go. Do x sub 1 bar minus x sub 2 bar plus the error, and this is the more accurate error. And then we've got this minus the more accurate error. So either one of these is fine. You can use this pair or this pair. Notice that they're not that different, but they are different in that third decimal place, especially for that upper limit right there. So it is making a bit of a difference. Let's see if MyLab Statistics likes the accurate one. So if I'm rounding to 3 decimal places, I get that answer for the accurate one. And then let's see what we get for the less accurate one, rounded to 3 decimal places. So our lower bound is the same, or our lower limit for the confidence interval is the same, either way. It's negative 0.601. But the upper limit is either 0.065 or 0.061. I'm going to use 0.061. That's the one calculated with the more accurate degrees of freedom, and see if MyLab Statistics likes it. It should like it because it is more accurate. And I bet it'll like it just fine. So I have negative 0.601 is my lower limit, and positive 0.061 is my upper limit. And they like that. Great. Oh, that was the end of that question. Okay, actually, let's go back. I guess that's all they wanted. They want us to come up with a confidence interval, and they also wanted us to do that hypothesis test. Now notice that mu sub 1 minus mu sub 2 equals 0 is in this interval, which means that the null hypothesis may be true. So if I were using this confidence interval to test the hypothesis, I would not accept the null, but I would fail to reject the null, which is exactly the same conclusion that we got using the p-value method above. So either way, we're getting the same answer, which is what we would expect.